Here's some more examples of solving trigonometric equations. This first one has reciprocal trig identities, so I'm actually going to change them both to be in terms of sine and cos. Cosecant squared x I can rewrite as 1 over sine squared x, and then cotan x I can write as 2 cos squared x over sine squared x is equal to 0. These both have the same denominator, so I can add the numerators together. All over sine squared x. And then the neat thing about a fraction being equal to 0 is that I can just set the numerator equal to 0. And now I can isolate cos squared x is equal to 1/2. And now I can square root both sides to isolate cos x. Now, the neat thing about square rooting is that I could have positive 1 over root 2 or negative 1 over root 2. So when I go to decide which quadrant my solutions are in, I actually have solutions in the positive cos quadrants, which are here and here. And I also have solutions in the negative cos quadrants, which are here and here. So I have all 4 solutions. My related acute angle is the same in each one, which is pi over 4. In quadrant 1, my solution is equal to my related acute angle, which is pi over 4. In quadrant 2, my solution is going to be pi minus my related acute angle. So my second solution is 3 pi over 4. In my third quadrant, I have pi plus my related acute angle, so my next solution is 5 pi over 4. And in my fourth quadrant, my solution is 2 pi minus my related acute angle, which means that my fourth solution is 7 pi over 4. This happens anytime you have a squared trig function equal to a ratio. When you take the square root, you have a positive and negative answer, which means that you get 4 solutions based off one related acute angle. The next 4 that we're going to look at here use identities to simplify first. So here we've got 8 sine x cos x minus 2. I'm going to recognize that I can actually write this as 4 times 2 sine x cos x minus 2 is equal to 0. This part right here is a double angle identity. I can write that as 4 sine 2x minus 2 equals 0. This is then going to allow me to isolate sine 2x is equal to 1/2. Now I can figure out which quadrants my solution is in. So the positive quadrant of A, and then the positive sine quadrant. 1 over 2 is going to be my opposite side over my hypotenuse, leaving root 3 to be my adjacent, which means that this related acute angle is going to be pi over 6. My solution in the first quadrant is going to be equal to my related acute angle, which is pi over 6. And my solution in the second quadrant is going to be equal to pi minus my related acute angle, which is going to be 5 pi over 6. Now, it's not really x that is equal to, because the whole argument of sine is actually 2x. So this means that my solution is going to be pi over 12. And then my second solution is going to be 5 pi over 12. Because my argument is 2x, that means that my period is actually compressed. The sine wave is going faster than repeating every 2 pi. So that means that I'm actually going to have additional solutions, which are my given solution that I found using the related acute angle, plus 2 pi divided by that k factor. So I have another solution at 13 pi over 12 when I simplify that. And then in my Q2 solution, I've got another repetition of the same value, starting from 5 pi over 12 and adding 2 pi divided by 2. 2 pi is the period, and this is my k value from my equation that I'm solving. So I have another solution at 17 pi over 12. So I also have 4 solutions to this equation here because of the compressed period. So let's take a look at another one, which we're also going to replace with an identity. Let's start by actually replacing both of them. So I'm going to replace sine 2x with 2 sine x cos x, and I'm going to replace cos 2x with cos squared x minus sine squared x, and I'm even going to replace the 1 with cos squared x plus sine squared x. What that's going to allow me to do is that these two cos squared x terms are going to cancel out, and these two are actually going to add together because they are like terms. So then on my next line, I have 2 sine squared x plus 2 sine x cos x is equal to 0. And now I could actually common factor out 2 sine x, which is going to leave me with sine x plus cos x is equal to 0. Once I have it split into those factors, I can actually say that 2 sine x is equal to 0, or sine x plus cos x is equal to 0. From my first factor, I'm going to get that x is equal to 0, pi, or 2 pi. Those are the values that make sine x equal to 0. And on my right side here, I'm actually going to move cos x to the other side. And then I'm going to divide both sides by cos x. On my left-hand side, this leaves me with tan x. On the right-hand side, this leaves me with minus 1. I know that tan is negative in the second quadrant and the fourth quadrant. I also know that 1 is one of my special triangles, giving me a related acute angle of pi over 4. That means that I also have a solution in my second quadrant of being pi minus my related acute angle. I also have a solution in my fourth quadrant where x is 2 pi minus my related acute angle, giving me an x value of 7 pi over 4. So I actually have 5 solutions for this equation: 0, pi, 2 pi, and then 3 pi over 4 and 7 pi over 4. My next example has 3 terms, and so my thinking originally is that I'm probably going to have to factor this, but I want to get it all in terms of sine theta. So I'm going to replace 2 cos squared theta with 1 minus sine squared theta plus 1, and then I'm going to simplify. So when I expand, I'm going to get 2 sine squared theta plus 3 sine theta minus 1 is equal to 0. I'm going to look at those a, b, and c values, and I'm going to recognize that I can't factor that, which means that I need to use the quadratic formula. So normally I would start with x equals negative b, but because my x in this case is really sine theta, I'm going to write that sine theta is negative b plus or minus the square root b squared minus 4ac all over 2a. When I evaluate that, I get that sine theta is minus 3 plus or minus root 17 over 4. And when I fully calculate that down to the decimal values, I get that sine theta is equal to approximately minus 1.7808, or that sine theta is equal to 0.2808. There is no solution for the first value because the right-hand side is greater than -1 or less than -1, and that is outside of the range of the sine function. In the second one, I know that sine is positive, which means I have a solution in the first quadrant and the second quadrant. My related acute angle I find by taking the sine inverse of 0.2808. Gives me a related acute angle of 0.2846. From that, I can find my solution in the first quadrant, which is equal to my related acute angle. And then I can find my second solution in the second quadrant by doing pi take away my related acute angle, which gives me my second solution of 2.857. My final example over here uses one of our addition formulas or subtraction formulas. Cos A, cos B, plus sine A, sine B can actually be simplified to cos of A minus B is equal to √3/2, which I can further simplify to be cos 3x is equal to √3/2. So I know that when cos is positive, I have a solution in the first quadrant and the fourth quadrant. Finding my related acute angle is going to give me pi/6 using my special triangle. This means that in my first quadrant, my solution is 3x is equal to pi/6 because of that k value in my equation. So that means that my first solution is actually pi/18. In my fourth quadrant, 3x is 2 pi, take away my related acute angle, which is going to give me 11 pi/6, which I then simplify to 11 pi/18. Now, because I have that k factor, I need to keep adding in factors of my period until I get all of the repeated values. So I'm going to start, I'll label these as x1, x2. I'm going to start with pi/18, and I'm going to add the period divided by the k value. This means that my next solution is at pi/18 plus 12 pi/18, which simplifies to 13 pi/18. And because I have a 3 in front, I'm going to check and see if I can actually add in one more multiple. So I'm going to try adding another 2 pi/3 to see if I have another solution within my interval. I'm going to get 25 pi/18, which is less than 2 pi. I can tell that if I add another multiple of 2 pi/3, so if I add 12 pi/18 again, I would get 37 pi/18, which is past my stated domain of 2 pi. So that means that I know I found all these solutions from that quadrant 1 value. So let's repeat the same process for quadrant 4. I'm going to take my starting value, so 11 pi/18, and I'm going to add 2 pi/3, which gives me an additional solution of 23 pi/18. And I'm going to check and see if there is one more solution in my interval by adding 12 pi/18 again, which gives me 35 pi/18, which is just inside my interval of 0 to 2 pi. And so I actually have 6 solutions for this equation: pi/18, 11 pi/18, 13 pi over 18, 23 pi over 18, 25 pi over 18, and 35 pi over 18.